faithfully sharing value by interpreting great books from around the world. Hello, this is Sally Talking Books. Today, we're interpreting the book Why for You. The subtitle is about the new science of causality. The author of this book, Judea Pearl, is a member of the U.S. National Academy of Sciences and an authority in artificial intelligence. Nowadays, with tech like big data and AI advancing, many folks think that enough data alone can solve any problem. But the author points out that current AI isn't truly intelligent. He believes you're smarter than your data because data doesn't get causality, but humans do.
However, the author isn't just focused on AI. Pearl's bigger ambition is to establish and promote a new field called causal inference.
The author argues this new field will impact all parts of human life, from new drug development and policy innovation to education models and fighting global warming. Before diving in, just a heads up, this book's pretty hardcore, involving lots of math and experimental models. The Chinese edition even includes a separate workbook to help grasp and solidify the concepts. This session will only cover the book's core ideas. If causal inference interests you, or you want to dive into the author's models, I highly recommend reading the original. Our talk will center on a key concept by the author, the ladder of causation. Ladder, as in the steps of a ladder. This ladder has 3 levels for causal inference: association, intervention, and counterfactual. These terms might sound confusing at first, but no worries, we'll break down each level, explain what the ladder of causation means, and show how this thinking affects decisions and life. The first level is association, which basically means finding links between different variables. So, a typical question here is, if I see something happening, what might happen next? For instance, if I get a fever with a cold, how likely is it I'll also have a headache? For association, we can use a more familiar word, correlation. In the development of correlation research, 2 figures are unavoidable: Galton and Pearson, who had a mentor-student relationship. Well, the British scholar Galton, known for evolutionary theory and being Darwin's cousin, was likely influenced by his relative. Galton was particularly interested in anthropology and statistical analysis, having designed a device called the Galton board. This Galton board, you might have seen similar setups in lottery games. It's a board filled with nails, arranged in a triangular pattern, essentially a pegboard. It has an opening at the top where you can drop small balls. Once a ball enters, it bounces down layer by layer before landing in slots at the bottom. For any single ball, each time it hits a nail, its bounce direction, left or right, is completely random. When you pour many balls in, a fascinating pattern emerges. Balls pile highest near the center, tapering off toward the edges like a small hill. This distribution is called the normal distribution. Today we know this normal distribution phenomenon is everywhere. For example, Galton's data on soldiers' heights showed normal distribution. Most were average height, with very few extremely tall or short individuals. Initially, Galton thought this board could model human inheritance patterns, but problems surfaced. If you lengthen the board by adding more nails, the distribution flattens and more balls land near the edges. If this mirrored real human inheritance, each generation would see increasing numbers of extremely tall or extremely short people. But we know human height distribution remains relatively stable. A century ago, there were no 3-meter tall people, and still none exist today. Galton even observed that tall fathers' sons tend to be taller than average, but not taller than their fathers. Similarly, shorter fathers' sons tend to be somewhat shorter than average. But he's not as short as his father. In other words, compared to their fathers, sons' height tends to be more average. Galton called this phenomenon regression to the mean, which means returning to the average, especially in height. There are many such regression to the mean phenomena in real life. For example, in some sports competitions, they select the Rookie of the Year, meaning the best performing new player in their first season. However, these Rookies of the Year might not perform as well in their second season. Another example is the saying, wealth doesn't last 3 generations, which is actually a form of regression to the mean. Galton kept trying to find a causal explanation for regression to the mean, and many others have attempted to analyze similar phenomena. For instance, when a rookie player's performance becomes mediocre later, experts might explain it as overconfidence or opponents figuring out their play style. Similarly, for wealth doesn't last 3 generations. Some claim it's because descendants become extravagant or incompetent, leading to wealth loss. However, the book's author points out that the regression to the mean process doesn't require a causal explanation. This phenomenon can be explained solely by probability rules. Nobel Prize winner Daniel Kahneman proposed a famous formula in his book, Thinking Fast and Slow. Success equals talent plus luck, and great success equals more talent plus more luck. Talent is a rare event. Luck is also rare. Someone being very tall comes partly from genetics and partly from good luck or environment. Their next generation inherits good genetics, but if the environment changes or luck diminishes, height regresses. Similarly, a player who wins Rookie of the Year is indeed more capable than average players. But to stand out among other equally talented newcomers requires significant luck. Then, in the second season, although equally skilled, they might not be as fortunate. So, their performance declines. By 1889, Galton finally understood this. The view he formed then was that not all phenomena have a causal explanation. After rejecting the absolute role of causality, Galton began collecting more anthropometric data, including height, arm length, head size, and so on. He noticed that tall people usually have longer than average forearms. Clearly, you can't say height causes arm length. There's just a correlation. And this so-called correlation is what the book's author refers to as association. Using our earlier expression, if you observe someone is tall, there's a high probability their arms are long too. If Galton started correlation research, his student Carl Pearson was more extreme. He wanted to erase causality from statistics entirely. Pearson believed all relationships were correlations, not causations. Over decades, Pearson built huge influence. In 1901, he founded the journal Biometrica, which remains highly authoritative in statistics today. In 1903, Pearson established the Biometrics Laboratory at University College London, which became the center of the statistics world.
By then, Pearson grew fanatical about correlation research, even suppressing dissenting men.
Schools of thought. According to colleagues, Pearson demanded absolute loyalty and forced dissenters out. Yet cracks appeared in Pearson's correlation empire because absurd correlations are easy to find. For example, a strong correlation exists between a country's chocolate consumption per capita and its Nobel laureates. Clearly, nonsense, since eating chocolate doesn't win Nobels. Pearson called these spurious correlations with no scientific meaning, but with slight thought we can link chocolate to Nobels. Wealthier countries consume more chocolate and have higher research capabilities. Thus, they produce more Nobel laureates. This causal explanation was fiercely resisted by Pearson, who saw causality as superstition. Pearson's stubbornness left him unable to explain such spurious correlations, causing followers to part ways. To tackle such spurious correlations, we climb to the second level of the ladder of causation, intervention. This concept asks, what effect will taking an action have? For example, if I take aspirin, will it cure my headache? Before taking action, before intervening, we must first eliminate confounding factors. Confounders are factors that simultaneously affect both cause and outcome. In analyzing spurious correlations, Pearson's key mistake was ignoring confounders. In the chocolate Nobel case, national wealth was the confounder, affecting both chocolate consumption and Nobel wins. Similar examples exist. Someone found high correlation between UK death rates and church weddings in certain years, meaning more religious weddings meant higher national mortality. Is God punishing happily married believers? Obviously not. Here the confounder was time or historical trends. During that period, both UK mortality and religious activity increased, creating false correlation. These examples show confounders are crucial for causal inference, especially in drug trials. Researchers must control confounders for credible conclusions. For instance, the author mentions Simpson's paradox, a famous statistical puzzle. A Dr. Simpson tested a new heart disease prevention drug. Surprisingly, results showed the drug harmed men and harmed women, but benefited humans overall. How is that possible? Let's simplify Dr. Simpson's findings. The trial had two groups: treatment group, 40 women, 20 men, and control group, no drug. The control group had 40 men and 20 women. Both groups totaled 60 people. In the control group, 12 of 40 men got sick, 30% rate. 1 of 20 women got sick, 5% rate. In the treatment group, 8 out of 20 men got sick, 40% rate. 3 out of 40 women got sick, 7.5% rate. That's a lot of numbers, so let's recap. Untreated men had 30% sickness rate. Treated men, 40%. Clearly, the drug harmed men. Untreated women had 5% rate, treated 7.5%, so it harmed women too. Based on this, the drug seems ineffective for both genders. But here's the weird part. Combining all data, the untreated group had 13 sick out of 60, 22% rate, while treated had 11 sick, 18% rate, meaning sickness decreased with treatment. For humanity overall, the drug appears effective. You might find this astonishing. We've listed the numbers in the transcript for your own calculation. Indeed, harmful to men, harmful to women, yet beneficial to humans collectively. If you understand confounders, you'll spot the issue. Gender affected both group assignment and outcome, a classic Simpson's paradox case. Because confounders distort results so severely, many researchers overcompensate by controlling excessive variables. Hence, research papers often include huge tables controlling gender, age, ethnicity, BMI, region, diet, etc. But the author argues this wastes resources and risks error. You might accidentally control the very factor being measured. So is there a better way to avoid confounders? Absolutely, randomized control trials. Let's explain this with an agricultural example. Suppose farmers want to know if fertilizer A outperforms fertilizer B. How should they test it? You might think it's easy. Just use fertilizer A on one plot and B on another, then see which yields more. But it's not that simple. Fertilizer effects mix with other factors like soil, water sources, seeds, climate, etc. Maybe the left plot was more fertile to begin with, or closer to water. Even planting sequence affects crop yield. In 1923, British scholar Ronald Fisher designed a method to verify fertilizer effects. This method, randomized controlled trials, centers on designing random experiments. He'd divide land into small plots, randomly assign fertilizers, then measure plant growth. This constituted one trial, repeated many times with fresh random assignments each round. Sometimes you'd get unlucky, assigning fertilizer A only to poor soil. Other times lucky, using it all on the richest land. But with more trials, say 100, each produces new random assignments. This ensures most times you're neither extremely lucky nor unlucky. Now you can exclude land or water factors and focus purely on fertilizer A versus B. Today, randomized trials seem obvious, but Fisher's design was revolutionary. All confounding factors cancel out through repeated randomization. Though randomization removes bias, we often can't conduct such experiments. For example, studying obesity's effect on heart disease. We can't randomly make people gain or lose weight. Or studying smoking and lung cancer, we can't randomly assign people to smoke for 10 years. When real-world problems prevent intervention, we need the third level of the ladder of causation. The third level of the ladder of causation is called counterfactual, meaning what if. Counterfactual means asking what would happen if something didn't occur. Typical questions at this level. For example, if I hadn't taken aspirin 3 days ago, would my headache have gone away? When thinking counterfactually, we can't directly observe or intervene. We can't travel back to stop ourselves from taking the pill.
and then return to see if the headache vanished.
So, counterfactual thinking happens only in the mind, inferring underlying mechanisms. Thus, counterfactual questions can be rephrased as, why would my headache have healed even if I didn't take aspirin? This question essentially asks why aspirin can cure headaches. The author believes this counterfactual thinking is key to human societal progress. A key to counterfactual thinking is identifying mediating factors. Simply put, a mediating factor is when A causes B and B causes C, so B is the mediator. To emphasize mediating factors' importance, the author cites a real historical case. With Columbus discovering the New World, humanity entered the age of exploration. However, sailors long at sea were plagued by a dreadful disease, scurvy. Between 1500 and 1800, about 2 million sailors died from it, until 1747, when James Lind, a British naval doctor, discovered that eating citrus fruits could treat scurvy. By the 19th century, the British Navy mandated all ships carry ample citrus, so scurvy seemed eradicated. However, a century later, when British explored polar regions, this historical disease resurged. At least 4 expeditions reported scurvy. In 1903, 5 members of Scott's Antarctic expedition reached the South Pole and died there. 2 of them likely died from scurvy. Why did this tragedy happen? Because doctors didn't truly understand how citrus prevented scurvy. In other words, they didn't know the mediating factor. Since Lind's era, people thought citrus prevented scurvy because of its acidity. Based on this causal inference, doctors believed anything sour could prevent scurvy. Initially, sailors ate Spanish lemons, then switched to cheaper West Indian limes as substitutes. These limes were equally acidic but contained only 1/4 the vitamin C. Worse yet, some started boiling juice for easier storage and transport. High heat destroyed the already low vitamin C, accelerating the mediator's failure. In 1875, when Arctic explorers drank lime juice but still got scurvy, doctors blamed canned meat bacteria instead. After prolonged confusion, Polish chemist Casimir Funk proposed vitamins in 1912. Not until 1930 did Hungarian physiologist Szent Györgyi isolate vitamin C, revealing the key to preventing scurvy. Szent Györgyi won a Nobel for this, finally clarifying the causation chain. Citrus provides vitamin C, which prevents scurvy. Once the mediator is identified, we can take more actions to influence outcomes. For example, if sailors run out of citrus, they can find other vitamin C-rich foods to fight scurvy. Of course, mediating factors aren't just mechanisms. They have deeper complexities. When A causes B and A plus B together cause C, mediator B can skew our analysis. Here's a concrete example. At a company, employee salary is determined by education and work experience. Say Xiao Zhang has a bachelor's degree and 5 years experience, earning $100,000 yearly. If he had a master's degree, what would his salary be? We can't make Xiao Zhang time travel to get a master's and reapply. This becomes a classic counterfactual problem. If this problem were yours, how would you analyze it? You might consider creating a formula. Salary equals coefficient A times education plus coefficient B times experience. Educational background can be quantified numerically. For example, bachelor's degree equals 1, master's equals 2, PhD equals 3. To find coefficients A and B, gather data from colleagues like Xiao Wang, Li, and Zhao, their education and work experience. After simple calculations, you'll get values for A and B. Then replace Xiao Zhang's education with master's in the formula to get his hypothetical salary. This method is called regression analysis, a common mathematical approach. Seems fine at first glance, but the author points out this analysis has a fundamental flaw. Being data-driven ignores causal inference. Looking closer at salary, we find a key factor: work experience. Here, experience affects salary, but also depends on education level. Higher educated employees spend more time in school, after all. So at the same age, their work years are shorter. Thus, work experience is a mediating factor. Specifically, if Xiaozhan had a master's, his experience would decrease by 2 to 3 years. This adjustment must be factored into the formula. Since this example's causal model and regression are simple, mediator analysis seems like a brain teaser, but it's fundamentally a different analytical framework. As the author states, regression analysis stays on the first level of the ladder of causation. Level 1 just observes data patterns. True causal inference, reaching level 3, requires understanding mediators and relationships.
After climbing all 3 levels, we've now learned to build accurate causal models and make causal inferences.
Finally, let's discuss how causal inference benefits humanity. The author argues causal models are essential for solving major human challenges, like achieving true artificial intelligence or AGI. Strong AI refers to intelligence that matches or even surpasses human-level intelligence. As a leading figure in AI, the author has long explored how to build such strong AI. In recent years, AI technologies like deep learning have achieved remarkable success in many fields. For example, AlphaGo defeated human Go champions, but the author notes current tech relies solely on massive data training, stuck at the first level of the ladder of causation. And to achieve strong AI, machines must understand causal models to think like humans, reflecting on errors and self-improving.
Beyond AI, the author argues much scientific research remains confined within statistical frameworks.
Their work often only addresses correlation, the first level of the ladder of causation. Level 1, causal models let scientists understand data interactions to truly answer why questions. The author believes a causal revolution will transform science, fostering greater prosperity. All right, that concludes our interpretation of why. Reading notes are below the audio. See you tomorrow.